initialized, ready to go, and then sort of come back, and the application and the component can interact with each other relatively directly. There is some mediation that goes on with Parlay to make this happen, but not everything in the world is going to go through this layer. There's some amount of direct interaction we want to be able to do. So what is this Parlay interrupt layer? So at a very high level, there's sort of four major concerns that we'll be thinking about. So one is just basic coordination of this federation of VMs. So there's interfaces to register a new VM, create VMs, destroy VMs, and manage VMs in various ways, so that the interrupt layer knows what VMs are available to it, knows what they can do, can start them up and bring them down. So the second major is metadata. So at the interrupt layer, what we're trying to do is define a fairly generic notion of what a resource is, and we have a way of attaching attributes to resources. And that's really all that happens, that the Parlay layer understands. And so then different languages and different VMs can use these attributes to express things about their types, functions, slots, which are effectively instance variables or class data variables, vtable data. And we also intend ways of hints. You can attributes to sort of say, this is a function of my language and it's a constructor or it's an accessor. And so if you have that kind of structure in your language and there's a similar structure in a different language, when the IDE sort of makes this match between the two languages, it can present this attribute to you in a way that's meaningful in your language. This is how you sort of map similar cross-language constructs without either language actually really knowing about each other. And in terms of the other concerns are basically data and control. So there's a subset of an object model, which I'm going to talk about in the next couple of slides. There's API dealing with memory management, certain extremely fundamental types like strings and primitives. The Parlay layer actually is really going to understand and automap between the languages. And for control, things about calling conventions and also cross-VM interfaces to deal with exceptions and exceptions that cross VM boundaries and stack crawling and stack walking and things like that. Okay, oops, wrong. All right. So there's a basic API that we think is enough for sort of relatively primitive level of interop. And then we're also thinking about extensions that enable a deeper cross-VM integration for places where performance is more critical. Particularly, we want to have relatively direct invocation of foreign functions. We don't want to have to cross down into the interop layer and do a relatively heavyweight operation every time you want to cross this VM boundary. And so I'm going to tell you a little bit about how we think that can work. We want to pass by reference, not by proxy where possible. And so actually allowing my VM to give your VM a direct reference to an object in its heap and then dealing with the consequences of that. One of the key ingredients to that is some amount of cross-VM cooperation for garbage collection. And this is a piece of the design where we actually had a meeting yesterday afternoon, and things are radically different than they were last week. So it's still very much an evolving thing. This effectively gives you, in a lot of ways, what you've done is you have a distributed garbage collection problem now. You've got multiple VMs, each with their own garbage collectors and their own heaps, and they want to pass references back and forth to each other. And you've got a distributed garbage collection problem, so you're sort of back to trying to solve some of those problems. So it's unclear whether that piece of it, what the right trade-offs are to be making there. So that's something that I'd be interested to talk to people about, especially people who, like Ben and Andrew, who know about garbage collection more than I do. Perry Chang is working on this, and there's some stuff about that. So.
Hasn't that problem already been solved with RMI? And it's a similar issue, right? Unless you don't want to serialize and unserialized data.
Right, we don't want to pass by value though.
Okay.
We want to actually pass the references. See, we want to preserve the semantics of this is a reference, actually pass a pointer to the object. And maybe we have to introduce a level of proxies to do that, but we don't want to copy. That's not what the language.
Usually when you think about distributed collection, you assume there's several heaps, fine, and that to communicate between one heap and another, a pointer is expensive because it's distributed. But here you don't have that second part.
Right.
And so all the assumptions on which most distributed collectors have been built don't apply.
Right. Yeah. So you can't add this great barrier for free.
Right. Something is cheaper than what they're right. So maybe there's both.
Right. So this is just so for objects. So part of what we want to do is we're actually going to allow people to pass direct object references across virtual machines. There has to be a certain amount of agreement to what an object actually is. And so for those types that are going to be exposed across VM boundaries, we intend on imposing some piece of an object model on this. And so what this picture is supposed to show is, here's an object. So things in blue are things that Parley doesn't care about. Things in orange are things that we expect. So you have some object. You have an object pointer. We expect the first word of that to be something like a class pointer. We don't actually care what it is. We want it to be a pointer to a hunk of memory of which there's a piece of it that's reserved for Parley at a fixed offset. And part of that is pointing to dispatch tables. So part of making a cross-language function call is if a VMA has a pointer to this object and it wants to make a call, there's a dispatch table here that's set up for calls from VMA to instances of this class. And in this dispatch table is where we can put sort of a impedance matching code. So when we come in here, we can generate, sort of lazily generate stubs that will deal with calling convention and sort of other object model differences between the VM that's making the call and the VM that actually owns the object. Hopefully that made sense. Now we can talk about it offline. But basically the idea is to make these cross-VM function calls more expensive than sort of a direct call potentially, because there's an extra indirect in here, and there might be some thunk code in here that does some impedance matching, but it's not that different from a normal call. You sort of get in here, and in the common case, where the VMs have compatible object models, compatible or potential common case where everything is relatively compatible, that thunk may not actually do very much. Okay, so something else we've been thinking about, which if the VMs are relatively close in their character, you might want to share some common components. And if you can do that, it might make some of these other interrupt issues simpler. In particular, JIT optimizers and backends and memory managers are relatively expensive to develop as such things go, and there's the potential for sharing these components across VMs that are relatively close to each other in character. So you could have a common JIT optimizer for a Java VM and some other VM that's relatively close to it. And the big advantages of doing this are sort of the obvious software engineering. Don't develop multiple JITs for languages that are really close to each other. It can reduce the footprint of the VM because you only have one JIT or two JITs instead of 10 JITs. And also, by having these components on both sides of the fence be similar, or be the same component, you actually can do a certain amount of, if I know you and I are using the same garbage collector, it's probably easier for me to deal with the distributed GC problem for the case of you and I than in general. Okay. So the current status of this is basically, so there's foils, and we've actually been working on this for a few months. We've done a fair amount of thinking about what has to be in this interrupt layer and how to reduce it to a relatively small set of functions that hopefully won't be too onerous to implement. So we've actually defined and implemented version 1 of this interrupt library, built a sort of dummy VM that you can start up and sort of probe into this interop layer to do things, mainly for debugging. Now we started to work on getting a CLR and a JVM implementation to also talk to this layer. And so that's the sort of initial target of this research project, is trying to take these two languages which are relatively close, two VMs which are relatively close together, and so the interrupt problems are probably not that hard. It is sort of evidenced by the fact that when people take the IKVM, for example, takes Java and compiles it into the CLR and then just runs it. So the language models are not that different from each other. So they provide a sort of nice easy case for us. And one of the things I was hoping to get from this workshop is suggestions for a sufficiently different third language to look at to really sort of stress some of these assumptions. These two are relatively close to each other. So that's pretty much the end of what I wanted to talk about, other than just opening up for discussion and getting people's sort of comments on how viable or useful you think this kind of architecture is, what VM should we be looking at, and another thing is scenarios to evaluate whether this is a good idea.
Story first about protection.
Story about protection.
Yeah, like.